Unit 6 is about gases. So remember, a gas uniformly fills any container, mixes completely with other gases, and exerts pressure on its surroundings. So pressure, which we'll talk about in a few minutes, is also force per area. So pressure is equal to force divided by area. And if you look at the units for force, it's newtons, and the unit for area would be meters squared. So a newton per meter squared is one type of unit for pressure. Now, gas laws describe and predict the behavior of gases. The kinetic molecular theory explains their behavior. So particles essentially are independent of each other and under standard temperature and pressure. So they're free to move, and they move in random movements, but in straight lines, random straight lines. The ideal gas law is derived from the model of the kinetic molecular theory. So what happens in a balloon, or what happens in our gas can here? As you blow air into the balloon, the air pushes against the elastic sides and blows it up. So in our gas can, there's air pushing on the inside of the can, keeping the structure of the can. The more you blow in, the pressure is exerted against the sides, the larger the balloon gets. If we were to remove the air, then the balloon would shrink. So if we remove the air inside our gas can, it shrinks because the atmospheric pressure on the outside now is pushing in, and there's nothing holding it up, nothing pushing back against it. Substances that exist as gases. You have the atmosphere, which is 78% nitrogen, 21% oxygen, and then 1% every other gas, including carbon dioxide. So really, our atmosphere is mostly nitrogen. It's a mixture of gases, and the atmosphere has become a very interesting topic of study because of environmental pollutions and the different problems we're now seeing on with our environment because of a change in our gases in the atmosphere. So here's a list of the elements that are gases at at standard temperature, which is 1 atm and 25 degrees Celsius. So notice that we have some diatomics that are gases. All right, our other diatomics, bromine is a liquid and iodine is a solid. You have our noble gases, which are our monatomic gases, one atom gases. Then you have a list of compounds. Notice that all the compounds are molecular. They're all covalent, not ionic, and that's because ionic has a stronger force of attraction, the positive negative. So that's a really strong force of attraction, so it pulls all the atoms into a tightly packed unit, which is our solids. The molecular formulas that you see here have either hydrogen bonding or dipole-dipole or London dispersion. So they're not as attracted to each other, molecule to molecule, so they're allowed to spread out a little bit more. The other thing to notice is that H2S and HCN are deadly gases. They're poisonous. And that most of the gases are colorless, with the exception of fluorine, chlorine, and NO2. NO2, nitrogen dioxide, is actually a dark brown color. Alright, so again, all gases share these properties. They assume the volume and shape of their container. They're the most compressible state of matter because the molecules themselves are the farthest apart. And gases will mix evenly and completely when confined in the same container. So it doesn't matter what section you take, it's pretty much evenly mixed. Gases also have a much lower density than liquids and solids because of the volume that they take up. The space between the molecules is so much larger than in solids and liquids. So measuring pressure, you use a barometer to measure atmospheric pressure. So you have the gas pushing down on our pool of mercury, And when the atmospheric gas pushes down on the pool of mercury, mercury gets pushed up into the tube. The gas that's in the tube then exerts a pressure back on that mercury until it stabilizes, until it's equal. The height of the mercury then tells us our atmospheric pressure. And at sea level, the atmospheric pressure reads 760 millimeters of mercury. So that is why millimeters of mercury is one of our units of pressure. Now, if we wanted to find the pressure of any other gas besides atmospheric, we would need to use a manometer. Now, that's where you have a sealed sealed gas here, and then the gas is exerting pressure on mercury. And then you have your atmosphere exerting pressure on the mercury. The difference in height then gives you the pressure of the gas. So in picture A here, our gas pressure is less than the pressure of atmospheric pressure. And in picture B, their gas pressure is much greater than our atmospheric pressure because it forced the mercury up the other side. Pressure is equal to the force per area unit, or unit area. We've already talked about how it's newtons per meter squared. Well, newtons per meter squared is also equal to a Pascal. Pascal is the scientist who looked at pressures and came up with it, so that's why Pascal is named after him. So 1 atmosphere is equal to 1,325 pascals. We typically convert that into kilopascals, but plain pascals is actually the SI unit. We also know that that is equal to 760 millimeters of mercury, or 760 torr. Torr is another unit named after the scientist Torricelli, who did some experiments with pressure. So you have ATM, which is atmospheric pressure, millimeters of mercury, torr, and then the SI unit, Pascal. In the United States, we use another unit for pressure, which is PSI, pounds per square inch. And down here is a conversion. Now, in Chem 1, we don't need to know this conversion. In AP, you do need to know this conversion. So make sure you have that one memorized. So if we were to convert then, for letter A, we would have 4.8 ATM. And we know that for 1 atmospheric pressure, we have 760 millimeters of mercury. That would give us 3.6 times 10 to the third millimeters of mercury. We do want to put that in scientific notation because we don't want to have to deal with all the zeros. For torr, 4.8 ATM is actually going to be the exact same number because torr and millimeters of mercury are pretty much the same unit. So we can just convert right to it. Alright, so for kilopascals, you'd start with 4.8 ATM. 1 atmosphere is 1,325 pascals. So that would give us an answer of 4.9 times 10 to the 5th pascals. Now that's pretty large. So if we wanted to convert that into kilopascals, we would take off times 10 to the 3rd, and we would have 4.9 times 10 to the 2nd kilopascals, which is a little bit more reasonable of a number. And then finally, if we want to convert to PSI, we take our ATM. Using our conversion, we know that 1 atmosphere is 14.7 pounds per square inch, and so we have 71 PSI. So just remember a little bit of review. T is for temperature, capital V is for volume, capital P is for pressure. You always want to make sure that you check your units, so it's going to be vital that you have numbers and units every single time you do something, and that the units cancel out. That will hopefully catch some of the mistakes that are common. The other thing to remember is that temperature must be in Kelvin, and that to convert to Kelvin we add 273. Alright, Robert Boyle is an Irish chemist who used a J-shaped tube closed at one end to study the relationship between pressure of a trapped gas and then the volume. The product of the pressure and volume for the trapped air sample is constant. And because it's constant, we get Boyle's law. Pressure, or P1 times V1 equals P2 times V2. It holds precisely only at very low pressure. So as soon as you start increasing the pressure, Boyle's law doesn't really hold true anymore, but it is true for our ideal gases. So if we were to look at a graph, you would notice that if you just did pressure versus volume, you get a curve. But if you do pressure versus, or volume versus inverse pressure, you would get a straight line. So that the slope is our constant, and that allows us to say V1 times P1 equals V2 times P2. So you need to remember the Boyle's law is Vp, and it's inversely related to each other. And a gas that obeys Boyle's law is called an ideal gas, and at the end of this unit we'll really talk about what happens when it's not an ideal gas, but for right now we're just going to assume that all the gases we talk about are ideal. Jacques Charles is a French chemist. He was the first person to fill a balloon with hydrogen gas and make a solo balloon flight. In 1787, he found that the volume of a gas at constant pressure increases linearly with the temperature. So when graphed, volume versus temperature, we get a straight line. So they're directly related to each other. And so Charles's law is V1 over T1 equals V2 over T2. So again, make sure that you know Charles's law is volume and temperature, and that they are directly related to each other. So just want to take this time to take a time out again. Remember, temperatures below at temperatures below 0 Kelvin, volumes would become negative. So 0 Kelvin is absolute zero. The lowest recorded temperature right now is 0.000001 Kelvin. So we're getting closer to absolute zero, but we've never reached it. Joseph Gay-Lussac looked at pressure versus temperature. He found that, it was a direct relationship to temperature. So if you were to graph pressure versus temperature, again, you would get that straight line. So P1 over T1 equals P2 over T2. If you were to take Boyle's law, Gay-Lussac's law, and Charles's law and put them all together, then you get the combined gas law. V1 P1 over T1 equals V2 P2 over T2. Be able to solve for each of those pieces. Just be careful when you're solving for T2. A lot of times students solve for the inverse instead of T2. Alright, Avogadro's law is not one that we typically touch on in Chem 1, but Avogadro is the same person as Avogadro's number. He found that equal volumes of gas at the same temperature and pressure contain the same number of particles. So if we look at our 4 balloons, even though we have different gases, they have the same volume, 1 liter, they're at the same temperature, 25 degrees Celsius, and the same pressure, 1 atm. That means they all contain the same number of moles. And if you think about your ideal gas law, if P is constant, V is constant, R and T is constant, that means N also has to be the same. And because moles and molecules are related through Avogadro's number, if you have the same number of moles, you're going to have the same number of molecules. So Avogadro's law, for a gas at constant temperature and pressure, the volume is directly proportional to the moles. So you can actually set up N1 over V1 equals N2 over V2. And if you were to graph it, it's a direct relationship. Alright, so suppose we have 12.2 liter sample containing oxygen gas at a pressure of 1 atm and a temperature of 25. If all of the oxygen was converted to ozone, which is O3, at the same temperature and pressure, what would be the volume of ozone? So if we set up a reaction here, we have oxygen being converted to O3, ozone. So we would have to balance it. N1 over V1 equals N2 over V2. So what we could do is, instead of doing 1s and 2s, we could use our molecules. So we could say the moles of O2 compared to the volume of O2 is equal to the moles of ozone over the volume of ozone. So we could say that 3, which is our coefficient, divided by 12.2 equals 2, which is the coefficient of ozone, divided by x. And then when we solve for x, we would get 8.13 liters.